Number of states in an ideal gas. Consider an ideal gas consisting of capital N particles confined within a box with edge lengths Lx, Ly, and Lz. Here N is supposed to be of the order of Avogadro's number. By considering the energy contribution from each quantum number separately and using approximations similar to those used in the text, show that the number of states in a given energy interval between E and E plus delta E is given by V to the n e to the 3 over 2n times a constant delta E. So V is the volume. Okay, so n is a large number. It's of the order of Avogadro's number. We have ideal gas that is in a box with volume Lx, Ly, Lz, and we're considering the contribution from each quantum number separately. Now, if this gas has a total energy E, since we have 3 quantum numbers per particle, Nx, Ny, and Z per particle. These are basically determined by or determining the wave vector k, if you remember. If you count the total number of degrees of freedom, we call this F. F is going to be equal to 3 quantum numbers per particle, capital N particles, so 3n. So we can calculate the average energy per degree of freedom. Epsilon bar, this will be the total energy E divided by 3 times capital N. And we also know that for each degree of freedom, we have a certain number of accessible states with energies less than E or epsilon. We have, well, as we have found in the previous problem also, the number of accessible states with energies less than E is equal to Li divided by pi h bar square root 2me. So this comes from the fact that we have energy is equal to h bar square k square over 2m, where I have h bar square, and so this is for one-dimensional case, it will be ni square pi square over 2m Li square. So I can be x or y or z. So that's the energy per degree of freedom. And from this, if you look at what the maximum value of Ni can be for energy less than E, you will find the number of accessible states. So isolate N sub I, so this will give you the number of accessible states. So that's what we did in the lecture. So we can now calculate the total number of states, accessible states, for capital N particles. basically phi for the total energy less than or equal to E, we have the number of accessible states for x E at energy E divided by, which is evaluated at energy E divided by 3n to the power n, because I have capital N molecules. Then I have the same thing for Y with average energy E divided by 3n per degree of freedom to the power n. And then I have phi z E divided by 3n to the power capital N. And so if I substitute what I know for these number of accessible states for energies less than E, I will have Lx divided by pi h bar 2m epsilon bar to the power 1/2 parentheses to the power capital N, and then we will do the same thing for Y and Z. Then I will have Ly divided by pi h bar 2m epsilon bar to the power 1/2 to the power capital N. And then for Z also I have Lz divided by pi h bar 2m epsilon bar to the power 1/2 to the power n. So you can see that this can be written as Lx, Ly, Lz Lx, Ly, Lz divided by pi h bar cube to the power n multiplied by 2m epsilon bar to the power 3n, 3 capital N over 2. And then we can obtain the number of accessible states for energy in the range E to E plus delta E, that is the density of states multiplied by the energy interval delta E. The density of states is the derivative d phi dE. So since I have phi of E now given as the volume divided by pi h bar cube to the power capital N, and then 2m the total energy E divided by 3n to the power 3n over 2. If you take the derivative, you will find that this is going to be equal to there is no energy in the first term, so v over pi h bar cube remains, and then I have also no energy in 2m over 3n to the power 3n over 2, but the energy to the power 3n over 2 will give me a 3n over 2 energy to the power 3n over 2 minus 1. Well, 3n over 2 is much greater than 1 because n is of the order of Avogadro's number, so we can safely neglect this minus 1 here. So I see that this is of the form a constant C times volume to the power n, energy to the power 3n over 2 approximately, because n is very large. And therefore, the number of accessible states for energies in the range E to E plus delta E will be this constant c v to the n e to the 3n over 2 multiplied with delta E, which is the result we would like to reach. Okay, so we're considering the number of states in an ideal gas. It consists of capital N particles in a box with edge lengths Lx, Ly, Lz. N is very large. By considering energy contribution from each quantum number, we want to know the number of states in a given energy interval. And because for a total energy E, if I have 3 quantum numbers per particle for capital N particles, total number of degrees of freedom is 3n, then the energy per degree of freedom is total energy divided by 3n. For each degree of freedom, I have a number of accessible states for energies less than E. And actually, for a degree of freedom, we should probably make this epsilon rather than E, because E we have used for total energy. So for each one, we have epsilon equals h bar square ki square over 2m. So that's basically giving us the number of states, accessible states for energies less than E as Li over pi h bar square root 2me. But we have capital N particles, so we have to evaluate these states and at epsilon bar and take it to the power capital N for capital N particles and multiply for x, y, and z. So we obtain the number of accessible states as the volume V divided by pi h bar cubed to the power capital M, 2m epsilon bar to the power 3n over 2. When we take the derivative of phi with respect to E, we obtain rho of E, the density of states, as constant C times volume to the power N, energy to the power 3 capital N over 2, actually 3 capital N over 2 minus 1, but minus 1 we can neglect, and by multiplying density of states with the energy interval delta E, we obtain omega E in the form suggested by the problem statement.